Okay, let's get started. Two announcements. No class this Friday. It's a federal holiday. And Lab 4 is due this Sunday. That's it. So today we will continue our discussion on SDN and one very important part of SDN called OpenFlow. So I want to talk a little bit about the history of SDN first. So in 2006, a PhD student named Martin Casado, maybe, he was a PhD student at Stanford University, and he has been working on network for several years. So actually, he got his bachelor's degree from Northern Arizona State University, at Flagstaff. So after several years of work, he went to Stanford for a PhD. So he started as basically the foundation work of SDN. And right now, in the community, people are calling him the father of SDN. So in 2007, he graduated, but actually the idea and the name of SDN was coming out from the OpenFlow project. And OpenFlow is part of SDN has been standard, and that will be the topic of today. So 2009, his group, his advisors, they published OpenFlow, the first version. Then later that year, they co-founded a company, and 3 years later, VMware bought that company for more than 1 billion. So VMware, we know that VMware is working on virtualization. So SDN is very related to virtualization because it has been widely used in data centers. And also it can enable the concept of network virtualization. Maybe that's why VMware bought it in 2012. So the market of SDN has increased a lot in the last 5 years. And it is predicted that by 2018, the market will be more than $35 billion. So if you join big companies, after you get a degree, you join Amazon or Google, and all of them, they are using SDN right now. So all the switches we can buy from the market now, the enterprise level switches, they all support OpenFlow. But like I said, OpenFlow is just a part of the SDN. So let me remind you the concept, some basic concept first before we dig into OpenFlow. So two very important concepts. One is called the control plane. The other is called the data plane. And the control plane decides how to forward packets, how to manipulate the packets. And the data plane actually performs those actions. So in traditional network, the data plane and the control plane, they are both baked into hardware, into switches or routers. So the switches, they can forward, they can filter, they can limit the rate and do some statistics, measure the packets, and they also need to discover other routers, decide which route the packet should take, and track the topology change of the network. So because each of the switches or routers, they are doing that individually, so they are running some distributed algorithm. Each of them, they are running their own algorithm, and somehow they are communicating with each other. So if you are taking the design and analysis of algorithm class, I believe it's 450. So in that class, you learn the many algorithms. And you may find that designing an algorithm, designing an efficient algorithm is actually very difficult. But all the algorithms I believe you learn in that class, they are centralized. They only run on one computer, one CPU, single thread. So if you want to design a distributed algorithm involving remote parties, that would be even more difficult. So that's why designing those kind of distributed routing algorithms very difficult, and they're not efficient, and a lot of errors. And on top of this data plane, control plane, there is another managed plane right now for traditional computer networks. So the managed plane are the IT, are the users. They try to configure the network. They try to configure all the equipments. So the goal of SDN is basically to separate the control plane and the data plane. And now for traditional networks, they are all baked in hardware. If we separate them, make the control plane software, it will be much more flexible. Even though it may mean it will be more costly, it may not be as efficient as before, but it will be much more flexible. We can enable network protocol involvement. So separating the control plane to software, that's why the idea is called software-defined networking. So the second goal is not only separate the control plane should be able to run any general purpose hardware. It can run on your MacBook, a server, or any PC. It doesn't have to run on a switch. The controller, the devices running controller doesn't need to have those network capabilities. They are just making decisions. And the third goal is to have some programmable data planes. What does that mean? So previously we have switches, we have routers, we have hubs. So when I talk about switches, I'm talking about traditional switches, layer 2 switches. So layer 2 switches, they only look at the layer 2 headers, the MAC address. And routers, they only look at the IP address. They're not flexible. So if we have a programmable data plane that can look at any field of the header, so we can do much more. It will be more generic. So in order to do that, SDN lift this control plane from the each individual switches or routers and consolidate all those control planes into one logically centralized controller. So then the controller needs to talk with all the switches, and that part is called OpenFlow. And also the switches, the data plane, that part is also called OpenFlow tables. So in traditional L2 switches, we have switch tables. In routers, we have routing tables. So basically, they do very similar things. They match the headers, then they decide what actions should be taken. They are just matching different part of the headers. So in OpenFlow, they used a very generic term, flow table, instead of a switch table, routing table. So that flow table can match any part of the headers. So also, with this design, the previous managed plane, which was used by IT's network administrators, can be replaced by application planes. So all the softwares can run on top of these controllers to control all the traffics. So humans, they only need to write network applications. Another advantage of this is previously each switches, they have to make their own decisions using some distributed algorithms for routing, for other purposes, because they don't have a global view. But now, the logically centralized controller, it says everything in the network. So the network is just a graph to the controller. So in this case, the application developers, they don't have to design distributed control protocols. So previously, we are using distributed spanning tree protocol for switches. We are using distributed Bearman forward algorithm for routing to discover shortest path in a network that's distributed. Each switch or router runs that. So those protocols, they are very complicated, but now we don't have to use them. We can just use, because the network, the controller, or it's called the network operating system, serves as a fundamental controlling block. It has a global view. It just say a graph of the network. So the applications on top of that can simply run djcastra to calculate the shortest path, which is much easier. I'm not sure if you learned those two algorithms in your 450 class. No? Yes? Okay. So you know this algorithm can be distributed, and this one usually is centralized, but it's much faster. So, and also with SDN, we can have applications. So there are APIs for applications to control the flows. So like I discussed before, there are two APIs in this design. One is the API for the controllers to communicate with the switches. And the other set of API is for the applications to call the controller's services. So this part has not been standardized, but the controller part, the controller to switches part has been standardized, and the protocols we are using and the switches, they are following the protocol called OpenFlow. So like I said, because of that, OpenFlow is just part of the SDN idea. It's not, so SDN is not OpenFlow. So probably the idea of SDN will stay there for decades, but the protocol of OpenFlow may be changed. So right now, the OpenFlow has been updated 4 or 5 times, but still there are a lot of issues. Even in our lab, we identify some problem in OpenFlow. We publish papers there. So I don't know. So some people are saying probably 10 years later, we're not going to use OpenFlow. But still, there will be a communication protocol between controllers and the switches. So right now, the standardized OpenFlow is this interface between the control plane, the separated control plane, and the data plane. So these are the switches. So now when I talk about switches, I'm not talking about layer 2 switches, not even layer 3 switches. We're talking about OpenFlow switches. They can look at layer 2 headers, layer 3 headers, even layer 4 headers, or even payload. So in all those OpenFlow switches, they have OpenFlow tables. So basically, this is called flow tables. This is a generic version of previous switch table or routing table or even firewall tables. It can be any of those. So on top of that, we have the control plane or the network OS, and OpenFlow is the protocol between them and the data plane of the switch. So obviously, this protocol itself should be protected. So the switches can only be orchestrated by authenticated network OS. So we use usually we use SSL or TLS to protect that part. And on top of that, we can run all kinds of applications, routing applications, node balancers, and they are going to install those flow entries into the switches through this controller. And this part of API has not been standardized. So usually if you read SDN articles, you can find other terminologies. Some people call this part the southbound API of SDN, collecting control plane and data plane. And this part called the northbound APIs of SDN. So there has been open networking group talking about standardize this part, but it has not been finalized. So right now, all those controllers, there are a lot of open source projects working on the controllers, and also a lot of vendors, they already provide OpenFlow enabled switches. So the controller part, they have their own APIs. There is no standard. So if you want to develop SDN application, probably that application is tied with some kind of controller. But because we already standardized this part, the controller probably is not tied with any switch. You can use it for any switch. So let's put everything together to see how it works. So first, the controller, or let's say the applications, when they want to manage any traffic, they need to manipulate the flow tables at the switches. So basically, each entry in that flow table is an instruction. It's something like one row in that switch table or routing table or even firewall. Basically, it's match and action. So whenever a packet arrives at one switch, the switch will consult its flow table to match the header fields in that flow table, then perform those actions. Besides performing those actions, usually they will update some statistics, some counters to say how many packets I have received for this flow, something like that. So if there is no match, this happens before. In firewall, if there is no match, usually it means the firewall should drop that packet. But here we're talking about a generic design. So if there is no match, the switch will forward the whole packet to the controller. Ask the controller to decide what to do next. Because the switches in this design, they are only the data plane. They do not make decisions. They only perform those actions. So we will look at the data plane first. So the data plane, basically that's the flow table, the generic table. So that table will match all kinds of patterns in the header fields, and it supports all kinds of actions, include the forward, drop, modify, and send to controller. So the switch one, so the previous layer 2 switch, usually they only have a forward or flat. They cannot change the packets. And the routers, usually they have forward. If it's a network address translation router, they can modify some fields. And if the TTL value drops to 0, they may decide to drop that. So if it's a firewall, usually it will have a forward and drop. But the OpenFlow, the Open Switch, they support all kinds of actions, including the previous actions. And also another one is sent to controller, just the forward the whole packet to the controller. So this is how OpenFlow entry looks like. There are rules just for matching. There are actions and statistics. So the matching part, they can look at the switch port, MAC address, MAC destination, VNet number, Ethernet type, IP sources. So this part, the switch port, is like the layer 1, physical layer information. And the MAC source address and destination, and Ethernet type and VLAN ID is like layer 2. So previously switches, layer 2 switches can also say this. And we can also have layer 3 information, IP source, IP destination, and protocol. And we can even have a TCP port number, TCP source number. So previously only firewalls, intrusion detection systems will look at those things. So at the very first version of OpenFlow, they didn't have this part, actually. They didn't have a layer 4 fields. So the latest version, they add this part. So maybe in the future, they are going to support any field in the header. So especially for our security guys, we want to know everything of the packet. So one of our research work, we have been extending the OpenFlow protocol and OpenFlow tables to match whatever we want to match in the headers. So because of this is a generic flow table. Now we can unify all kinds of different boxes. So if you want to use your switch as a layer 2 switch, or then you just need to have a entry in your flow table, just match the destination MAC address, and the action would be forward or flat. So if you want to use this switch, the OpenFlow switch as a router, then you probably want to match the destination IP address. So sometimes you only want to match the network part of the IP address, and the action will be forward. Or sometimes you can set field. You can change those fields. If you want to do a firewall, then you can match IP addresses, TCP, port numbers, and you can do allow or drop. If you want to do a network address translation, then you want to match IP addresses, port numbers, and you can rewrite those IP addresses and port numbers. So use the set field functionality. So here is an example. This is a switching. This is just one entry in your OpenFlow switch. So the OpenFlow switch in this case is still generic. It is doing a lot of things. It is doing switching, it is doing routing, it is doing firewall filtering, but this one entry is only doing switching. So this one will match any packet from any physical port, from any MAC source, and the destination MAC address is specified here. And for any packet from this MAC address, we will forward to port number 6. So this is just a switching. And in this case, in the OpenFlow switch, it is not really recording a switch table there. So this can be that switch table, but if you want more states, usually you should put those states remembering tasks in the controller, not in the switch. So if you want to do routing, so for any packet has this IP destination, we want to forward to a specific port. And if it's a firewall, it will be from any of the packets has a destination port 22, we want to drop it. And this can also be used for VLAN. So VLAN is actually a layer 2, layer 3 protocol. We discussed a little bit last week. So that's usually the switches, the traditional switches that supports VLAN is called an L3 switch. And in this case, they will have a VLAN ID and decide where to forward those packets. So I will use one example to show you how everything works in OpenFlow or SDN network. So let's first look at a legacy network. So in this network, we have 4 switches. They are connected with each other. So actually, maybe even here, there could be a physical link. But when the switches, they are connected together, they are going to run the minimum spanning tree protocol to decide I will block some of the physical links because we don't want to create circles in the loops in the network. So let's say this is a logical network we have. We have 4 hosts in the network, each of them directly connected to a switch, and the switches are connected together. So there is a host 2, and we assume that all the switches, they don't know anything at this moment, and all the hosts, they don't have any cache at this moment. So host 2 wants to communicate with host 1 using ping. So host 2 pings host 1's IP address. So in this case, host 2 first need to broadcast ARP request packet. So the ARP request packet will be flooded in the whole network because they are switches, they are not routers. So they will just simply forward this to all the hosts. So all the hosts in the network will receive this ARP request. Then host 1 also sees this packet and compares its own IP address with the IP address host 2 is asking for. Then it sends back an ARP reply saying, I have this IP address and this is my MAC address. So previously, it was a broadcast to all the hosts in the network, but the ARP reply is only a unicast from host 1 to host 2. Then the host 2 will remember that in its own ARP cache that this IP is associated with this MAC address. And then it will send a ICMP echo request. And this echo request will be directly sent to host 1. It's not a broadcast. And then host 1 will reply this. So this is what we started in the first half of this semester, how layer 2 and layer 3 works. So now we're talking about doing the same thing in an OpenFlow network. So still, we assume that the controllers has no information of anyone, and all the switches, their flow tables are all empty. And the hosts, they don't have any cache. So we want to do the same thing. Host 2 wants to ping host 1. So first, host 2 will send out an ARP request, same as before, because the SDN, we're not changing the hosts. We're only changing the network devices, the switches, the routers. So when switch 1 receives this ARP request, what will it do? It doesn't have any entries in its flow table right now. It doesn't make decisions. It will only do perform actions. And the switch doesn't know what actions it should take because its flow table is empty. So it will forward this packet, encapsulate everything to the controller. And that is called a package in message. So the controller will receive this ARP request. And some application in the controller developed by network administrators will check this message to see how to respond. So in this case, the controller will say, oh, this is a ARP request. So you should just simply forward this, flood this. Then it will send back the packet to the switch and tell the switch, you should simply flood this packet. Then the switch will flood this ARP packet to the other two switches that are connected with switch 1. So those two switches at this moment, they don't have any entries in their flow table either. So they will send this ARP message again back to the controller. And the controller will do the same thing. Ask them to simply flood this to the network. So for switch 3, because it is collected to another host, it will flood this to host 3. And for switch 2, it will send this to host 1 and switch 4. And when switch 4 sees this packet, it will talk with the controller again to ask for instructions. And eventually, it will forward this packet to host 4. So then, all the hosts in the network receive this ARP request, and only host 1 matches its IP address with the request. Then host 1 wants to reply this back to host 2. It should be a unicast. So host 1 will send the up reply back to switch 2. And at this moment, switch 2 may already have a flow entry there, which was installed previously by the controller. But that entry was used to match the first up request message. So probably there is no entry to match this packet. But you can see that here is very tricky. It depends on how the controller installs that flow entry. The flow entry can be very specific to previous packet, or it can be very generic. In this case, we assume that the controllers and the applications on the controllers try to be very fine-grained. So right now, when the up reply comes back to the switch 2, there is no entry to match with this. The switch 2 will forward this packet again to the controller, and the controller will check this is an up reply, and you are supposed to forward this to switch 1. So it will first packet out, send the whole packet back to the switch, and also add another flow entry here, saying whenever you get an up reply message from this host, you should forward it to here. So after that, switch 2 will forward it to switch 1. So it will not be flooded in the network. And switch 1, if it doesn't have a flow entry to match with that, it will do the same thing, talk with the controller, and ask the controller's help, and the controller will ask it to forward it back to host 2. So after that, host 2 will have this entry in its own up cache. So it's the same result as the previous legacy network. So the hosts, they don't really know they are in an SDN network because we're only changing the network part. The host, they are still using the same protocol. Then the host will send the ICMP echo request, and maybe there is still no flow entries. Then the controllers will decide what kind of flow entries should be installed here in all those switches. So basically, this is how it works in OpenFlow. So you can see that it seems like it's much more complicated than before. But the advantage here is the controller knows everything. It has a global view. Even though it's more complicated, actually it enables a lot of applications and increase the network utilization rate before. Because previously, even if there is an error in this network, because everything is distributed, it's very, very difficult to identify those problems. So one problem we discussed before is loops in networks. So technically, there should not be loops in networks. Otherwise, some packets will be forwarding in the network forever, even though we have TTL to stop that. But if there is no loop in the first place, we don't need TTL. Or if someone set the TTL value very high, the packet is still going to loop in the network for a very long time. So at internet scale, it's very, very hard, or even in an enterprise network, in a data center, it's very difficult to identify those loops. There has been a lot of research talking about how to identify those loops at each switch using some distributed algorithm, but there was no perfect solution. But with SDN, because the controller says everything, if there is a loop, it's just a loop in a graph. It's very easy to identify those things. So this is how OpenFlow works. So on top of OpenFlow, we have that controller part. So right now, there are many open source controller projects. The popular ones including Floodlight and Lox. I think Lox was the first one. So logs was a C++ and a Python implementation. It was published in 2008 in a sitcom paper. Yeah, so it's kind of like the first one. Then OpenFlow is based on Java. It's really popular right now. So in the next class, we're going to talk about a little bit about the SDN controllers. We're not going to cover application part too much because it's still it's not very clear how things will evolve there. Then we will talk about the security problems of SDN and OpenFlow. There have been many errors being found in those areas. Any questions? Yeah.
In the previous slide, why we need this Linux controller? Because now the controller has a global view.
So technically, we still need to run some kind of a spanning minimal spanning error, but it doesn't have to be distributed. The purpose is that every now the switch will
any transfer of packet from host 3 to host 4 should directly go via switch trains and host. Why?
So that's very good actually. So in those cases, the minimal static tree might be dynamic. It may not be static like that. Yeah, it's possible.